on Riemannian optimization by Melanie Weaver.
Thanks. And thanks to the organizers for the opportunity to speak. So I will talk about constraint optimization on Riemannian manifolds. And just let me start with briefly recalling why we are interested in Riemannian optimization. We've seen some nice applications and use cases earlier today. But one other way to motivate Riemannian optimization is that in many applications, especially if we think about machine learning, we encounter data with an explicit or implicit non-Euclidean structure. So we can think of data like graphs, strings, or matrices. And in such cases, it can be beneficial to represent the data in a space that naturally aligns with its geometry. And then if we want to perform an optimization or machine learning task, to adapt those algorithmic tools to the specific space. And in the optimization context, one very interesting aspect that we can make use of is geodesic convexity. So especially for matrix valued problems, some of which we saw earlier today, those and that are non-convex in Euclidean space, we can actually, with the right choice of metric, turn those into convex problems on a suitable Riemannian manifold, and that then benefits us when we want to perform an optimization task. So the examples that we will see in this talk are mostly for matrix valued problems. So where we have to optimize a matrix valued function. And for such problems, we can use tools from Euclidean optimization, where the class of matrices that we are working with typically enters as a constraint. So maybe we are optimizing subject to an orthogonality constraint, or we have some constraints on the rank, for instance. But we could also use tools from Riemannian optimization, where we rephrase the problem on a suitable manifold, which encodes that specific constraint. So for instance, for a positive definiteness constraint, that would be the manifold of positive definite matrices. So, and then in the Euclidean setting, we can use tools from unconstrained optimization, and that has received a lot of interest. And there are lots of classical algorithms that have been explored in those settings. But if we look at some specific applications and problems that we might want to solve with such techniques, then we see that oftentimes there are actually additional constraints that we would have to handle. So in addition to the sort of basic constraint which tells us which manifold to work on, we might have interval constraints or equality or inequality constraints, which are not directly being handled by the unconstrained optimization methods. So in those settings, we would need, it would be nice to have constrained optimization methods that can directly handle such additional constraints. And before we talk about such methods, I just want to briefly recall geodesic convexity. I know we've heard a lot of that already earlier, but I just want to define it. So if we have a function defined on a Riemannian manifold M, then we say that it is geodesically convex if it fulfills essentially the same usual convexity condition that we use in Euclidean space, but now with respect to a geodesic on that manifold. And in the optimization context, just as in the Euclidean setting, this gives us the guarantee that we have a unique global optimum. So for classical optimization algorithms, such as Riemannian gradient descent, we know that from any feasible initializations, those algorithms will converge to that global optimum, meaning that we can get nice global convergence guarantees. And oftentimes this also helps us to quantify the rate of convergence, so gives us a chance at deriving non-asymptotic convergence guarantees. And we already said in the matrix context, it's especially interesting to look at problems which are non-convex in Euclidean setting, but where this reformulation on a Riemannian manifold gives us geodesic convexity. And some examples for that are, for instance, the computation of Riemannian centroids on the manifold of positive definite matrices. So that's a special instance of the Cauchy-Mean problem. Also the computation of Braskamp-Lieb constants that we've heard about earlier, or the computation of generalized eigenvalues, for instance. So in this talk, as I said, we will focus on constraint optimization. So just to clarify the class of problems that we're looking at. So we have a function defined on a Riemannian manifold, which we assume to be smooth, but not necessarily geodesically convex. So we will see that some of the results also apply to geodesically non-convex functions. And we require that the minimum of the function that we're trying to compute lies in a compact and geodesically convex subset of the manifold, which we will denote as script x. And our goal is to efficiently compute a solution to this problem. And for the remainder of the talk, this is what we're going to talk about. So we will introduce an algorithm on Riemannian manifolds which can directly handle constraints. We will also look at the convergence, at what convergence guarantees we can get for that algorithm. And besides sort of a general analysis, also look at some specific settings, especially stochastic and finite sum settings, which are important for machine learning applications. And we will talk about what are the bottlenecks if we want to make this algorithm practical. So if we want to actually implement it and use it in practice, and also look at one sample application that shows us how to make this algorithm practical on one specific example. And everything that I'm going to talk about is joint work with Sofrit Sra at MIT and based on the 2 papers in the footnote. Okay, so to get a general idea how we could define an algorithm on Riemannian manifolds which can directly handle constraints, we can look at what has been done in the Euclidean setting. Of course, such a basic problem as constraint optimization is very well studied in the Euclidean setting. And in the literature, we see that there are essentially 2 classes of algorithms that are popular, that are being used, projected gradient methods and also projection-free methods. Projected gradient methods are essentially extensions of gradient descent style methods to the constraint setting. So the basic idea here is that if in iteration k we are at a point xk, then we evaluate the gradient to find a feasible descent direction and then perform a standard gradient descent update. And this, of course, doesn't take the constraints into account, which means that this update might carry us out of the feasible region, here shown in blue. And in that case, we have to project back onto the feasible region. So we have to construct some projection. And depending on the geometry of our constraint set of the feasible region, this might be easy to do, or this might be expensive. In cases where it is expensive, it's interesting to use a projection-free method which can directly handle constraints. And here the probably most popular method is the Frank-Wolf algorithm, which works as follows. So again, in iteration k, we are at a point xk. We evaluate the gradient to find a feasible descent direction. And then we call a subroutine, which we call the linear oracle. And this subroutine will compute a point in the feasible descent direction, which just fulfills the constraints. So in our example here, that point zk, which is returned from the linear oracle, lies on the boundary of the feasible region. And then we linearly interpolate between our current iterate and that point zk, and then step along that line with a certain step size, sk, which is typically chosen to be something like 1 over k. And then if we assume that our feasible region is convex, then any point along that line will be in the feasible region, meaning that we will never step out of the feasible region and therefore also don't have to worry about projecting back onto it. And then again, depending on the specific setting of the problem, it might be difficult or it might be easy to compute that the solution of the subroutine. So in practice, what one usually does is to compare the cost of computing those projections with the cost of solving the linear oracle, and then based on that, decide what might be the best type of algorithm to use. Okay, so that was for the Euclidean setting. The Riemannian gradient descent algorithm is very well studied on Riemannian manifolds. So that extension to projected gradient methods, which handle constraints only indirectly, is sort of easy to do, but it turns out that on manifolds it can be difficult to compute those additional projections. So it's worth looking into extending those projection-free methods to Riemannian manifolds as well. And to define such an algorithm, we essentially have to look at the two key components of the algorithm, so which is of course the linear oracle, and then the way we construct the update step. So first thing to note is that, of course, instead of the Euclidean gradient, we now evaluate the Riemannian gradient. And then for this interpolation step, we are now constructing a geodesic on the respective manifold, with a starting point being our current iterate, the endpoint being the point zk that is returned from the linear oracle, and then the speed of the geodesic will be at the gradient at the current iterate. And that allows us to write down a Riemannian equivalent of the Euclidean Frank-Wolf algorithm. And then what can we say about the sort of general convergence? We can adapt the proof techniques that we have for the Euclidean Frank-Wolf algorithm to Riemannian manifolds, and then show that that algorithm converges at a sublinear rate. So this means that after k iterations, we are on the order of 1/k close to the optimum. If we have a geodesically convex objective, then that would be the global optimum. If we have a geodesically non-convex function, that's of course only a local optimum. And then to put that convergence rate into perspective, so that recovers an iteration complexity comparable to what we know for the Euclidean Frank-Wolf method, and that's also comparable to the rates that we get for the Riemannian gradient descent in the general case. So like in the Euclidean setting, we could think of this as, okay, we need about the same number of iterations to reach a certain accuracy, and then we can look at the cost of each iteration. So if we can solve the Riemannian linear oracle very efficiently, then that would turn this into a practical algorithm. But before we focus on this problem of solving the Riemannian linear oracle, let's look at some special cases and what we can say about the performance of the algorithm in those settings. So if we have a strongly geodesically convex objective, meaning that we fulfill this condition. So the first part of this condition is just the usual, is equivalent to the definition of geodesic convexity that we saw earlier, just now written with respect to the inverse exponential map and not with respect to geodesics. And then we have this additional term here, which characterizes the strong convexity. So if our objective fulfills this stronger assumption on convexity, and if we know that the optimum does not lie on the boundary of the feasible region, then we actually get linear convergence. So then this algorithm is very fast. In the Euclidean setting, this problem of when Frank-Wolf methods have a fast linear convergence, it has also received a lot of attention, and there are different assumptions that have been studied under which such faster rates can be achieved. But to our knowledge, only this strong convexity assumption does translate to the Riemannian setting. Some of the other results that are known in Euclidean settings don't really have or are difficult to channelize to Riemannian settings. So especially with applications in mind, we might also think about how we can adapt such algorithms to specific classes of objective functions that we encounter in applications. So the first one are stochastic settings, where we want to optimize a black box function. So the difficulty here is that we don't have access to the underlying structure of the function that we want to optimize. And then finite sum settings. Those occur in many different applications. So if you think of empirical risk minimization or maximum likelihood estimation, there you typically have objective functions which are large sums over component functions. So here, if you think about computing the gradient of functions with such a structure, then you have to average over a sum of the gradients of all of those component functions. And so if M is very large, that can be computationally expensive and also introduce a bottleneck into the algorithm. So how can we deal with those two settings? For the stochastic setting, here the difficulty is, since we don't have access to the underlying function, we of course also don't have access directly to the gradient. We can only estimate it over samples that we draw. So our Riemannian linear oracle will have this stochastic form. And then here we can again take inspiration from the Euclidean setting and look at how these stochastic settings are dealt with in the Euclidean setting. And here what one typically does is to use a Robbins-Monroe approximation of the gradient, so use a batch estimate, and the same we can do in this setting. And then by carefully controlling the batch size, we can keep the gradient estimation error in check and recover the sublinear convergence guarantees that we had earlier in the general deterministic setting. For the finite sum setting, where we want to control the cost of computing the gradient, we can use a different gradient estimation technique. So instead of in each iteration computing the full gradient over all of those component functions, we can just take a subset of component functions and we can just recompute the full gradient every couple of iterations, and then in between compute the gradient averaged only over a subset of the gradients, so which significantly reduces the cost. And such approaches are called variance-reduced approaches. So we can also adapt those to the Riemannian setting, and then by carefully controlling the size of those subsets, and after how many iterations we recompute the gradient, we can again keep the estimation error in check and recover the global sublinear convergence rates. And we have also looked into like a recent improvement of that estimation technique. So those has originally been studied for the Euclidean SGD, so stochastic gradient descent. And there it was shown that it's actually not necessary to ever compute the full gradient if you want a sublinear convergence rate. It's enough to just iterate, to just switch between different sets of sample sizes, one a little bit larger, and then choose smaller sample sizes in between, and that still recovers the sublinear convergence rate. And a similar analysis can be done for the Riemannian Frank-Wolf method, again by carefully trading off these sample sizes. Okay, so to summarize, those techniques, especially in the finite sum setting, allow us to circumvent the computation of full gradients, significantly speeding up our methods. We do pay a little bit in the convergence rate. So as I said, we do recover a global sublinear rate, but it drops from on the order of 1 over k to 1 over square root k. This comes from the estimation error that we are making, even though we are trying to carefully control that. Yeah.
So all of them have, like, sorry, what is the convergence rate for all of these? If they're all
the iteration complexity is 1 over square root of k.
But for which ones? Because the first one should be 1 over k, no?
So those are orbital complexities.
Oh,
so this is the cost of each iteration, and then iteration complexity means what accuracy do I reach after how many iterations.
Oh, I see. And then and this is all square root 1 of k is for all of them?
So yeah, so this is for the deterministic one where I compute the full gradient, and then if I use the gradient estimates, this drops to 1 over square root of k. So for all of them. Okay. Yeah, so it's slightly less efficient, but we'll actually see that in the numerical experiments. The faster computation of each iteration overall wins out and makes those faster. Yeah. Okay, so now let's talk about the crucial subroutine, the Riemannian linear oracle. So in the Euclidean setting, one aspect that has contributed to the Frank-Wolf method being so popular is that this subroutine is convex and relatively easy to solve. In the Riemannian setting, unfortunately, the subroutine is non-convex. So we have to think a little bit more careful about how to solve that in practice. Two sort of ideas that come to mind on how we might solve this is, first, we could use some numerical solver, some off-the-shelf method, get some approximate solution, and then hopefully keep this in check to retain our sublinear iteration complexity. Or we could look at special cases and see if there are better ways of solving that subroutine. So since it is non-convex, there's not much hope for having sort of a general recipe for solving that efficiently in each case. But it turns out in special cases, there are faster ways of solving that subroutine. So, but first for the, if we only solve it approximately, so this condition would mean that we would have an exact minimizer for the linear oracle. And then if we put an error term here, we can call this delta approximate minimizer. And then with an adaptation of the previous convergence analysis, we see that if delta is small, that doesn't actually hurt us very much. So we retain the sublinear iteration complexity and then just have this small factor entering here, which depends on delta. So as long as we have a sufficiently good numerical solver, which allows us to relatively efficiently compute a delta approximate minimizer, then that should work pretty well in practice. What we have to keep in mind is that those numerical solvers have to be called in each iteration of the algorithm. So overall, it's going to be still quite expensive. So it is worth it looking into smarter ways of solving the linear oracle. And I want to just give one example where we can actually solve it very efficiently in closed form. So the example that I want to talk about is on the manifold of symmetric positive definite matrices, where our script X, our constraint set, are interval constraints. So those are here defined with respect to the Löwen order. So recall that we say X is larger or equal to L in Löwen order if X minus L has only non-negative eigenvalues. So that introduces a partial order relation on positive definite matrices, which allows us to define interval constraints. And then this is how the linear oracle looks in this case. So here we have just inserted the Riemannian gradient and then the inverse of the exponential map on that manifold. And some of the problems that we mentioned earlier are actually of that form. So including the Riemannian centroids, a special case of the Kauscher mean problem, and then also Wasserstein barycenters on the Gaussian density manifold. So this Gaussian density manifold is also called the Bors manifold, as isomorphic to the manifold of positive definite matrices. So therefore we can phrase this problem of Wasserstein barycenters also of that form, and that has some interesting connections to optimal transport and also sampling. So that's something that also recently has received quite a bit of attention. And in that specific case, we get the following closed form solution. In this talk, I cannot go into too many details about how to arrive there, but if you're interested, it's in the paper. So we get a closed form solution for this subroutine. So we don't have to call a numerical solver. In that case, we can just implement the closed form solution, which is much more efficient, of course, than calling the numerical solver. And to see how this then works in practice, let's look at one specific example. The problem of computing Riemannian centroids on the manifold of positive definite matrices. So the objective that we have here is as follows. So we have a collection of positive definite matrices, AI, which might have weights associated. And then we want to minimize this barycenter problem. Delta R here is the Riemannian metric on that manifold. And recall what we said earlier, that this is one of the interesting problems that's non-convex in the Euclidean setting, but with this choice of metric, it is geodesically convex. So by using our Frank-Wolf methods here, we get global convergence guarantees. And then where do we get the constraints from here? So we all know for real numbers, we have the means inequality. We know that the geometric mean is lower bounded by the harmonic mean and upper bounded by the arithmetic mean. And this relation also translates to matrices. And fortunately, both the harmonic and the arithmetic mean can be computed very easily in closed form. The geometric mean, the geometric matrix mean, unfortunately not, since matrix multiplication does not commute. So as soon as we have more than 2 matrices, this cannot be computed in closed form anymore. Hence, this being a good use case for Riemannian optimization. And then our algorithm looks as follows. So we already said we can easily pre-compute the harmonic and the arithmetic mean. And then in each iteration, we would compute the Riemannian gradient. We have this subroutine, the linear oracle, which we solve with the closed form solution that we just saw. And then we construct our geodesic with a step size, which we again set to like 1/k. And here are some results for different generated inputs. So here we see in blue the sort of standard Riemannian Frank-Wolf algorithm, and then also here included some of the stochastic variants that we've seen. So notice that has a finite sum structure that we discussed earlier. So here we can use these estimation techniques to lower the cost of computing the gradients, and then we also see here that in fact translates to faster convergence. And then we compare here against some other methods, Riemannian optimization algorithms in the literature. So those are variants of the Riemannian gradient descent algorithm, and we see that we're pretty competitive compared to those. We also see that we reach a pretty good accuracy with those methods. We do lose a little bit with the stochastic methods that work with gradient estimates, but even with those, we're at a reasonably good accuracy. Okay, and that's the end of my talk. So we talked about Frank-Wolf methods for projection-free optimization on Riemannian manifolds and discussed some different settings, both general deterministic settings and also some stochastic settings that are a bit more interesting for applications. And we've seen that those algorithms are practical if we can solve the Riemannian linear oracle efficiently. And we've seen one example or one class of problems where this is the case. We have some others in the paper. And in future direction, I hope to explore applications of that, especially in machine learning contexts more, and also in generally look at more systematically at how we can efficiently solve the linear oracle for other matrix manifolds and other constraint sets, maybe some of the initial examples that I shown for a start. Okay, thanks. Yeah.
The slide that you compare, so this comparison here is. So this is in terms of when you're talking about accuracy here, you run all this over in the same number of iterations or in the same amount of time for your algorithm. Because you're explaining that before, if you have the same number of iterations, the accuracy is already theoretically supposed to be worse, right? But then what matters is the total time it takes to.
Oh, yeah. So this is plotted with respect to the computing time. Yeah, but then we did give them a max number of iterations, right? I mean, you could run it forever, right? But you have like some max number of iterations after you stop it. Yeah, so that's maybe not so easy to see here, but yeah, you do see if you run everything the required number of a similar number of iterations up to some round of errors, you do see that they reach a similar accuracy. Yeah.
Right. So like if you let them run for a particular number of time.
Yeah.
I see.
Yeah, so but this is here just to make it comparable to the performance plots. This is all shown with respect to the computing time, but I think we have in the paper also for to just show it with respect to the number of iterations.
Well, but I think this is the more interesting, right? Because what you care about in the end is how long you run your algorithm, not the number of iterations.
Yeah,
So,
yeah.
But even then, the deterministic ones are better. So this is showing that if they run by the same amount of time, you get more accuracy.
Yeah, that's to be expected. You also see that for if you use the if you use the gradient estimates, you have a little error, especially if you once you get close to the optimum, the approximation error of the gradient will introduce an error, right? So this flattening out sort of the stochastic version, you also see in other stochastic optimization methods. It's something very typical you see, because once you're close, right, the approximation error will have a significant impact.
I see.
Yeah. So that's a very typical behavior of stochastic algorithms. Yeah. So typically there you have to, if you use that in practice, have to be very careful to build in stopping criteria, right? Because otherwise just the error of it will make you like circle around the true optimum.
Oh yeah, true.
Yeah.
Okay.
Did you compare this to a more just gradient descent like MBO, where you do like a diffusion and projection step instead of doing like a constrained optimization on the manifold along the geodesics? You can also do like diffusion in the ambient space and then project.
I have not compared it against that. No.
Oh.
Yeah. Yeah. So this is our comparison to optimization algorithms that like really run on the manifold, but yeah, it would be interesting to look into some of these other methods as well. We also, this comparison doesn't include any comparison to Euclidean methods, for instance. Right, so even though that's a non-convex problem, in the Euclidean case, you could use Euclidean methods and compare against those. So this is really just a comparison to Riemannian optimization algorithms. But yeah, that'd be interesting to see.
Could you show again this this result, where this theoretical result where you solve the optimization problem up to a fraction and then you still got convergence, please? Right. What is m of theta?
Oh, yeah, I should have mentioned that. So that's called the curvature constant. So that's like a sort of a hyperparameter that would depend on your objective function. So for instance, yeah, so it has to do with like the Lipschitz constant, the smoothness of the function, for instance.
But in which way? Does it kind of contain second derivatives, or what? I mean, how is it defined?
Yeah, in a sense, it's like the second order, quantifies the second order error in a sense.
Okay, so because in a certain sense you already did quantify a little bit the second order by your strict convexity condition, right? That is also the one-sided second order control.
Yeah.
And now you're having, now this M contains kind of also a second order control from the other side? Or, I mean, how is it actually defined?
It's like, so we have it in the paper. Yeah, it has to do with the convexity, as you were saying. And it can also be bounded with respect to the Lipschitz constant. So we have some, I'm just summarizing that here too. I mean, essentially you could write like on the order 1/k, and then you have some constants coming in that depend on the objective function, which I here summarized with that curvature constant. And then I'm just writing that out here to show the impact of that delta. But yeah, that can be much more carefully defined what exactly the constants are in the iteration complexity.
I'm just wondering, because since, I mean, some of these numerical analysis applications, I know the merit is exactly that you get convergence results which do not depend on kind of further properties like the curvature of the underlying space, like higher order derivatives of phi, but just rely on strict convexity. And so, but here, that might be in your case hidden in this constant M of fine.
So it does not depend on the curvature of the space.
Does not.
Yeah. But yeah, it certainly, yeah, so it's independent of the space, but it depends on the properties of the objective function. Yes.
And does the curvature of the space play any role, either theoretical or in practice, or it doesn't really matter?
No, for this result it doesn't.
And have you tried the samples? Yeah, for reason on space manifolds with positive curvature and negative curvature?
No, actually I haven't. I've only tried it on Hadamard manifolds.
And that's negative.
Yeah. So I mean, most of the results that I showed, also like the convergence result, like this is a convergence result. So those would work for any Riemannian manifold. But yeah, for the numerical experiments, we mostly focus, like if you look into the paper, we mostly focus on problems where you can actually solve that linear oracle efficiently. And I'm not aware of an example for positively curved manifolds. Yeah. Yeah, but you could run a numerical experiment and then just use a numerical solver for the separate and then try that. Yeah.
Where was that? But it's like the speaker.